should we start?
Yes, for me, yeah.
I think we have about 76 people right now, and people are trying to enter. Okay, so I would like to thank everyone for attending this event and welcome you to our second Tech Talk on microgrids. My name is Hussam Samkari and I'm the IEEE Palouse Vice Chair. We have a lot of officers joining us from the IEEE Palouse. We have Pavan, the Treasury, Asad, the Secretary, Alab, the Membership Developer, Steve is the Webmaster. And IEEE Palouse is hosting a series of Tech Talks on microgrids. There will be more than maybe now 4 webinars streamed on Zoom. This is the second series or the second session. IEEE Palouse invited speakers from both industry and academia to talk about the challenge and applications of microgrids. The duration usually around an hour. Also, for the future events, information about each session will be posted. Please follow IEEE Palouse. We have our website, Facebook, LinkedIn. And I would like to note that IEEE Palouse is part of IEEE Region 6, which include Moscow and Lewiston in Idaho and Pullman in Washington. Our second session today is about DC microgrids. We are honored to have Dr. Josep Guerrero. He is an IEEE fellow, and he is working at the Center of Research on Microgrids, Department of Energy Technology at Aalborg University. He received his bachelor degree in telecommunication engineering and master degree in electronic engineering, and his PhD degree in power electronics from Technical University of Catalonia, Barcelona. Professor Guerrero is an associate editor for several IEEE transactions. He has published more than 600 journal papers in the field of microgrids and renewable energy system, which are cited more than 50,000 times. He received the Best Paper Award of the IEEE transaction on energy conversion for the period of 2014 and 2015. He has awarded by the Climate Analytic former Thomson Reuters as a highly cited researcher with 50 highly cited papers. In 2015, he was elevated as IEEE Fellow for his contribution on distributed power system and microgrids. Please welcome Dr. Guerrero, and you may start.
Yeah, thank you very much for the introduction and the organization for this seminar, and for everyone here. I can see also a lot of new people and maybe other people, new faces, but I'm going to, yes, today I'm going to talk about DC microgrids, even if I'm going to talk about many other aspects. Here you have also our website of the Center for Research of Microgrids. So also you can find much more information here. My 4 words is, please don't believe a word what I'm going to present here. Yeah, if maybe there's many mistakes or just personal assumptions, please verify everything. Yeah, this is also, I will say, our aim, to verify everything, right? And I will say that this is something that we have today to do in our daily basis. Try to verify things and experience yourself. Second things is that, yeah, it's true. I'm really very curious from when I was 10 years old for electronics, and I was very active ecologist. Yeah, a little bit. Yeah, you know. One of the things that I like to do is, of course, music. I studied also 5 years in the School of Music, playing with several bands. And I like, by the way, practical things. So also this is one of the products that I finalized after my PhD, right? Right now it's in the market. It's a UPS system that can be parallel operation, which is, as some of you know, it's one of my favorite topics, how to put things in parallel without making huge explosions. And then after some years living in Barcelona and looking for a better weather, I moved to Denmark. So here you can see my team. We are 50 people, around between 15 and 20 PhD students, 10 postdocs, and a number of also staff, all of them working in microgrids. You will understand also why our lemma is microgrids seriously affect your brain. Is something that you're going to see in the next slides. We built also laboratory facilities. All these laboratory facilities, we try to emulate microgrids here. So a number of converters to emulate here a microgrid. So this is indeed a multi-microgrid laboratory that we built years ago, and still nowadays is ongoing with a number of, let's say, projects. Yeah. Here, everything about soldering or building, it's made in another lab. We have a workshop. That's why you can see that this is extremely clean, and this is clean because safety is very important in our labs. Yeah, you just see the mushroom buttons. We have a MATLAB Simulink to compile your ideas, and all these cabinets are well earthed and closed to avoid if there's any explosion. Everything is under control, let's say. We have also a mushroom button here of general safety. If something happened, we just disconnect the lab. Nobody has the key, just the technician, and it comes just once per day. So it will be off the whole day. The normal days, let's say, without explosions, what we are is just playing with software, and then download this software over digital signal platforms. And those digital signal platforms are interacting with a number of inverters. In our case, we built setups with 4 inverters, and then we reproduce, and we have in our labs around 10 of these setups. So this means that each of these setups has around 10 kilowatt, and we can parallel 10 more, so it's around 100 kilowatt laboratory right now. So this is the things that we do. We put a number of microgrids in parallel, and also we emulate everything about, let's say, generation, battery systems, and loads, but all the electric part is real. Smart meters are real, switches, transformers, and so on. It's only this part here in the bottom, which we have, let's say, in the loop. We cannot say that it's hardware in the loop, but let's say that what we have in the loop is the generation, storage, and consumption. And this way we can also make experiments like having multiple microgrids connected in one point, or we could also have number of microgrids that could be spread around, and then we could, let's say, build a virtual power plant. Maybe you know that right now in Europe, virtual power plants are becoming more and more important. And yes, we are in the country in which right now we already pass through the 60% of renewable energy. So that means that the electricity, 60% it's coming from renewables, and we are proud of that. And around 50% it's just coming from the wind. We want to still push it more and more. And that's why also we are devoting to do these kind of things, not only for wind, but also solar, and to have more about energy efficiency. This is also our IoT microgrid laboratory. It's a house, a demonstration house. I don't have here the pictures, but if you have the interest, of course, you can. I can show you. After many years researching microgrids, I decided to also become a prosumer. And a prosumer is not only putting solar panels in your roof, because this is something that you cannot control, because the solar panels are just injecting all the power to the grid, but also I install my own electric vehicle charger and my car. which is an electric vehicle. Some people ask me, what about your other car? Sorry, I have no other car. So like a doctor taking my own pills, I went there inside this personal, let's say, story. And I did like Dr. House. Yeah, Dr. House, if you are, personally, I'm a fan of this man. And you can see 90% of the cases are always lupus. And I will say that is something like people studying control. 90% of the cases is with a PI control, you can do everything, right? I'm sorry for the people who are studying very complex controllers. They have also their application, I will say. So I just pick one sentence from this TV series, very important. Dr. House said, if you want to do something, if you really want to do something, you will find a way. Otherwise, you will find the excuse. Yeah, excuses. No, in my country, not in my place, no, because. So I don't want to hear more excuses. I want just to integrate also what I'm doing, right? Other things, yeah. We talk a lot about artificial intelligence, but artificial intelligence, and now I come also to talk about how a lot of people is trying to apply artificial intelligence in microgrids. Artificial intelligence try to mimic, let's say, what we have in our brains, the neurons, but are we sure that we know how the brain works? It's really a question because it's important. Every time we wake up with our brains and we go to sleep with our brains. So sorry, even if tomorrow you are not studying microgrids, your brain still will be there, right? So that's very important. What we want to know about our brains is that really we have three brains. We have the mind, we have the heart, and we have the gut, which is the, let's say, all the digestion part. Here we know that in the mind, we know today that we have 80,000 million neurons, but in the heart also we have neurons, 40,000 neurons. And very curiously, they are activated when you have feelings of love, when you have feelings of understanding also, and when you have also feelings of hate, they are active. Yeah, today we know. And also we know that our digestion part have around 500 million neurons, the same amount of a brain cat. And this is really amazing. That's why many people right now are looking at your intestine bacteria. And they see how these intestine bacteria have direct effects over your psychology. Yeah, there are amazing tests right now exchanging bacteria from the intestines of rats. You have one rat very active, another very passive. They interchange and automatically the behavior also interchange. So we have here these three brains in which we have also neurons. And that's very interesting because when you see the chakras, and I can see here there's a lot of people coming from India, and you know it better than me, all these areas that you call chakras are really very much populated by neural networks. And this is really amazing. So what we have here is that we don't have a system that we believe in the past that it was a brain that controls everything. It's really a distributed system. Emotions, feelings, thinkings, right? Okay. So there's a lot of things to learn from India, I will say. Another thing, in the past, we hear that our brain, we can use just 5% of our brains. We just use 10% of our brains. Sorry. And we have to be very relaxed about that. We indeed use 100% of our brains. So don't worry, be relaxed. However, we can just use 2% simultaneously. So it's like these neural networks are blinking all the time, yeah? But simultaneously, because of limitation of glucose and oxygen, only 2% can be, let's say, enlightened simultaneously. And this is because we just have 4 watts here. Yeah, we have an electric brain, right? We know that. However, we can see that even though we use 100%, normally we use similar neural network paths. And that's why it's very difficult to change. It's complicated, not easy to change. You want to change your behavior and it takes time, but it's possible. And we know that this is possible thanks to what is called also neuroplasticity. Yeah. Another interesting thing, inside our minds also we have three brains again. So we have the reptilian brain, yes, something very, you know, action reaction, finding opportunities. For instance, this is very interesting because right now also people that study business, they are looking at this specific brain because it's the brain that allows, it's the brain who's always trying to look for a chance and just action reaction. It's the brain that you use when you want to buy something. So it's very important for people that are making business. So advertisements are really focused on that brain. The other brain, which have 200 million years, is the limbic brain, and is the one who is developed by the mammals. So for instance, your dog or your cat, they have already this limbic brain. And this is about emotions or feelings, right? And then the more, let's say, young brain is this that have only 100,000 years, which is the neocortex. And this is the rational part. However, we know that many times our decisions are taken by emotions. Why? You can take a look on these numbers. 200 million years over 100,000 years. It's clear that the decision is taken by this old guy. And then the rational part will come with the justification. Yes, I took this decision because, and you justify that. What I have to tell you is that also this part, the frontal cortex, is doing something amazing that in not other animals we can see. We are able to go to the future. So we predict the future. For instance, in 2 days, what I'm going to do. For instance, I'm going to have a trip. All right. So I come back to the present moment and I start planning to do it. This in other animals, you cannot see it. And this is amazing because in this neocortex, you can really make planifications. So then the decisions, you can take it based on this, going to the future, going back to the present moment and take the decision. This is something really unique, and that's why it's so amazing to study the human brain in our case, right? Also, we know things about stress. We hear a lot of people saying stress is not good. Well, according to this curve, which was discovered by Nixon and Yerkes and Thompson, moderated levels of stress are good because you generate dopamine and you generate noradrenaline, so you are more, let's say, in a more alert state, and you are able to be motivated and to learn more things. However, if these levels of stress are increasing too much, then you enter in distress, and you can enter also in burnout. Yeah, you can see a lot of people today still very anxious, and you are anxious because of the future, right? So we have two things here, two problems. One is to be very anxious, to have a lot of stress because you live in the future, and the other is to be depressed because you live in the past, right? So this is something that also we know it maybe for more than 4,000 years. The present moment is what gives you the happiness. However, we are always, you know, because of we have this frontal cortex, we go to the future, and it's good to go to the future, but then you have to go back to this present moment and to use it in a positive way. Other amazing things we know nowadays, the same areas in which we feel trust, when we trust in someone, for instance, they are activated, these three areas. The same areas are the ones that are activated when we have fear. So it's not possible to feel trust and fear at the same time. I think this was just a study done last year. So really, neuroscience is going in a very fast dimension, in a dimension that we never dreamed before. Look at something else about our empathy systems. We have the logic empathy, so we understand how this person is suffering, so we can give some response, or we have also the emotional empathy, which is based on our mirror neuron system. Yeah, someone is suffering, so automatically our neurons are reproducing this feeling, and we feel also the same, right? A little bit more on the emotional part, a little bit more on the limbic area. What else we know is, like, of course, we have these 4,000 neurons in our hearts, and there is a communication between the heart and the brain. Today, we know that there are more information traveling from the heart to the brain than from the brain to the heart, according to this paper published in 2014. This was by the Institute, Heart Math Institute in Germany. So we know that also our heart is able to generate hormones. In the past, we didn't know that. The hormones that are able to generate our heart is these two ones, amitriptyline and the oxytocin. When you think about oxytocin, that's very interesting because it's exactly the hormone that a woman is generating when the woman is waiting for a baby, and are the same that you generate when you feel love, trust, or fidelity. And this is something that today we measured, and we measure many other amazing things. You see, the heart rate. Some people believe the heart rate must be something stable, fixed, and this is not true. In average, maybe needs a stability, but it's changing all the time. And why it is changing all the time? Because what we need to have in our body is the blood pressure to be constant. Because the blood pressure needs to be constant, your heart rate is just changing to adjust it. The way that you change your heart rate, it's telling us how is your emotions. You can see here, the heart rate is how it's changing when you are in a state of incoherence, frustration, anxiety, worry, irritation. You can see a non-periodic waveform with a lot of harmonics here. However, when you have feelings of positive emotions, appreciation, love, courage, you can see that it's almost a sinusoidal. Almost no harmonics here, very stable, yeah? So this is, I will say that this is very interesting also. So we can see these two things first, just by looking at how is this heart rate changing, we can see how are our emotions, and at the same time, how there's a coherence between the waves that you have in your brain and the waves that you have in your heart goes in coherence. There's a lot of studies that we have today nowadays. But also I want to go a little bit further. Today we know that the electromagnetic field of the heart, it's 5,000 bigger than the one in the brain, and can be measured at 3 meters, even farther, depending on the measurements that you are using. And it has been also tested that in certain moments, different hearts can be synchronized. For instance, two lovers together, they tend to be synchronized. People singing in chorus, they synchronize also heart rhythm and also the way that they breathe together, and many other experiences, like for instance, dogs with kids. Once they are together also without touching each other, that's very important. You can see that they also enter in coherence, and etc. So I will say that this is really an amazing field itself. And it's very important for every one of us. It doesn't matter where we come from. How this impacts microgrids, I'm going to show you a little bit later when we talk about control, because we are talking about how we control our bodies here. DC microgrids, yes. Here you have an amazing example of DC microgrids. This is a microgrid supporting 1 megawatt. So that's not something small. This is in Sentai, and it's supporting a hospital, and it's supporting also the telecom system there. It's photovoltaic systems, 1 fuel cell, and a couple of gas turbines. Sentai is very close to Fukushima. This is the structure of this microgrid. You can see it's basically a DC link. And if you know something about UPS systems, this is kind of an online UPS system. And in parallel, you have kind of the same, but working on DC. DC from the solar PV to DC to the batteries to DC loads, because we are supporting telecoms in this side. So I will say that this is really very nice and symmetric design. But what happened the day when I said Fukushima? I know that some people start to think about 11th of March 2011. Yeah, that day we had the tsunami, and this tsunami causes really a huge impact. What happened with that microgrid that day? You can see that day was, of course, connected to the grid. It was the outage from the grid, and the microgrid was working one whole day in Ireland just with solar power and batteries. The gas engines were disconnected due to the mechanical, it was just tripping after the earthquake. After one day, they just reconnect the gas engines. So still, this microgrid was operating for 3 days in Ireland, supporting the hospital. It was very important at that time. And also people could use the mobile phones and to call their families. Just one example how these kind of technologies can help disasters that also were unfortunately produced also by other technologies. So you can see here also what we call in power systems the resilience curve. The resilience curve means that I come from performances which can be very high, let's say 100% of performances of my power system. Then I come with a disaster or an extreme event. This means that I have a decrease of the performances depending on how much is the disaster. And then I can just recover it back to another level of performances. Yeah, imagine, for instance, that here we are just working with solar and battery system, then we have the gas generators, and then we can recover after some time again. So that's very important to see how also microgrids can help to improve the resilience curve in power systems. Yeah. Going from the detection, which is very important to detect that there's a natural disaster or other kinds, and finally going to the mitigation and how much is this time also is sometimes very, very critical. Another example of DC microgrids, what happened with data centers. Some of these data centers are working, let's say, inherently in DC, because data center, basically they need a server or a number of servers, and all these servers have a number of voltages to, let's say, adequate. Here you can see 12, 5, 3.3 volt, and then you even have some point of load converters to put it back, to put it down to almost 1 volt. So finally, this is like a front end, and the front end is converting from AC to DC. If you think about the typical, let's say, solution is you just buy an online UPS system. So you have a rectifier and the battery and inverter, and this is just one pack. So you just install it and start working. What is the problem of this is that you are using here a number of conversions. Let's say here around 4 conversions. And if you think of a better solution, and this was an issue in a project, it's to think that these 2 conversions, DC to AC and then going from AC to DC back, it's really a loss of efficiency. So if you just neglect these parts and you just make a DC line, for instance, in that case was a 380 volt on DC, you have a 9% of improvement just neglecting this inverter, and then you have between 2 and 5% of improvement, depending on how you load it, when you just substitute the front end with a simple DC-DC converter. So we have around 15 to, let's say, 14% of improved efficiency. And the other interesting thing is, like, because you have a number of point of load converters, this voltage is not necessary to be well regulated. So that's also very nice, because you could optimize the voltage that you have here according to how much is the voltage that you need. So you can always go to this optimum point But for the people who's very, let's say, fans of having optimization algorithms, I'm saying, don't worry, it's not necessary to have such a complex system. It's just you make your voltage dependent on the load that you have here, and then naturally you'll reach more or less a reasonable efficient point. Intel did some studies also some years ago, and they built one facility for data center. It was a demonstration plant on DC and the same structure on AC to make, let's say, a comparison. After it was built, the improvements were 7% on efficiency and 6% on savings. So final conclusion is, all right, it looks that it makes sense if you want to do from scratch a DC data center to go in this direction, but if you want to make a retrofit, maybe it doesn't pay off. That's why you can see also now new data centers are going, some of them to DC, but not all data centers are going to be retrofitting. Interesting parts of when we talk about DC microgrids, we can have different elements with converters, and each of these elements have different functionalities. So it's not the same when I have a battery system that when I have, for instance, solar or wind conversion. So this means that they have really different characteristics. And then it's not the same when I have, for instance, one converter connected to the grid. So that's kind of different animals that we have in this ecosystem. No? For instance, when we are talking about having solar PV, for instance, many times it's interesting to work on the maximum point, like this, let's say, parabolic BI characteristic. However, if the voltage increases so much, means that maybe the system is overload, so we have to pass to a voltage control mode. Because we may have many other devices also working on voltage control mode, then maybe we can group them in order to share the power. So we have basically this kind of a little bit strange characteristics, which allow us to work on MPPT when the voltage has a lower levels, and on voltage mode or group mode when the voltage is higher. And these ideas are just taken from AC grids, you know. When we think about an AC grid, we just work on frequency. So we look at the frequency. If the frequency goes up, means that I have more generation than consumption. So this means that then I have to just regulate the power that I'm injecting. Maybe what I will do is to work as a grid forming, while if I see that the frequency is going down, maybe I have to inject more power. So kind of the same thing you can see here in voltage. Ideas that are developed on frequency control can be easily translated to voltage control. Another interesting thing is that we can see also some of these concepts a little bit messing names, you know. When we talk about group control in DC, it has been also developed for many years in something called adaptive voltage positioning. Adaptive voltage positioning has been used especially in small converters, point of load converters that are connected to digital loads to avoid having this kind of spikes. Imagine that this is a computer, and the computer or a microcontroller, and the microprocessor here is working full load and then suddenly goes to sleep mode. Then you have with a huge slew rate dropping down the current and then going up again. And this creates these spikes that our microprocessors don't like, because they basically destroy the CMOS. Yeah. In order to avoid this, what we do is if we add this group controller, when the current goes up, then the voltage automatically goes down, and vice versa. So you don't have these spikes anymore. This very interesting, let's say, area has been called also adaptive voltage positioning, this kind of control. And for instance, Intel came with a patent some years ago called enhanced adaptive voltage positioning. Yeah, but those are just variants from this very basic idea. Group control that can be also named adaptive voltage positioning. So please take care if these two names finally are kind of the same here. Another name that you can find is also virtual resistance. Indeed, when you think about DC, an adaptive voltage position, a drup controller, or a virtual resistor are exactly the same. Exactly the same. So please pay attention on this, because sometimes you read some documents and maybe they can mess these three concepts. Another interesting thing is like the same way that in AC power systems, they have, let's say, drups. We have also our drups in DC, but also we have what we call also secondary control. In an AC system, secondary control is developed by observing how is the frequency, and depending on the frequency, I will see if my system is overloaded or not. If the system is increasing the frequency, then okay, I will put more power in. If the frequency is going down, I will put more power in. If the frequency is going up, means that I'm injecting too much power to my loads. Here I do kind of the same. So look what we are doing. When I see that my voltage is going down, automatically I will send the reference back to each of these drup controllers or virtual impedance, if you think, by means of this term. I can do this by two different ideas. One is to do it in a centralized way. So I just have my central controller, the same as big power systems do, or I can do it in a decentralized way by using consensus algorithms, multi-agent systems, or whatever the control structure you want. Once this is built, you can think about what we call also tertiary control. And the tertiary control, what is looking is on how to optimize the system. So if you think also about our brain, what I explained before, primary control is our, let's say, reptilian brain. Secondary control is like our limbic brain. And when you think about the tertiary control, the energy management system is the frontal cortex, right? This one that is able to go to the future, see what will happen, come back and take a decision. This is basically what an energy management system can do. Go to the future, come back, optimize, take a decision, right? Once I take the decision, I can, for instance, decide if I want to import or export power. And I can do this with many kinds of artificial algorithms, artificial intelligence algorithms that could give me finally a reference of current or power to exchange with other microgrids that could be there, or a stiff DC grid. It could be a DC distribution grid. Right now, 380 volts on this is becoming more and more a standard. So this is one test that we did. Two DC-DC converters sharing the load without the primary controller. We just connect the primary controller, the virtual resistor. You can see that they are sharing the load. However, the voltage is deviating because of these primary control characteristics. Then what we did is we add another term to exchange power with the main grid. And you can see that what we did is to import current. So you can see how it's going a little bit more down. Yeah. This is by using the secondary control. So even if here we share the power, we start the primary control, you can see that there's a deviation of voltage. We come back. And then here in this point, we increase the power. And then you can see how we restore again. Yeah. Kind of the same of an AC power system. So some people also believe that in the grid you have 60 or 50 hertz which are stable all the time, right? The same of the hertz beats. Now we know that the hertz rate is not constant. It's not like in the frequency of the grid 50 or 60. It's changing all the time to regulate the blood pressure. In the grid, what happened? We are also changing all the time the frequency to regulate the balance between consumption and production of energy, right? So it's kind of the same. Here we are doing exactly the same idea that we have on AC systems here in DC. Yes. Finally, here you can see also that we are also able to import some power from the grid. In that case was 20 amps. And what we do is just, we have a stiff grid here. So what we are going to do is to reduce the voltage. So automatically I will have injection of current. So now we have here, let's say, the 3 levels of control, these 3 levels, which are also, when I was talking about the brain, the 3 levels of the brain, kind of the same, let's say, right? It's amazing how the number 3, it's appearing in many places, no? Also religion, society, etc. Let's go. What happened with DC at home? It was a lot of expectations, yeah, about that future houses are going to work on DC, and we don't see this happen here in Europe, and it's going to be very hard, because basically the problem here is that we need a rectifier, and this rectifier, which is connected to the main grid, is always operating in a point which is changing all the time. So losses are going to play a big role here. So in a study we did in Denmark, we demonstrate that unless you don't have solar panels, huge battery system, and let's say independence from the grid, then in the best of the cases you can get 10% of increase of efficiency. Otherwise, and this is the case in Denmark, we didn't extrapolate to other countries, but you could do it in your country, we have even losses up to 10% higher than having your home in AC. It is not happening here, but right now we are running projects. For instance, one exciting project in Madagascar to develop DC nanogrids. So in cases that you have houses that you have just consumptions of 100 watt to supply laptops, cell phones, and maybe a TV. So a huge reduction of consumption and just supplying with solar panels and battery systems. Then starts to have to make sense, and some devices, like for instance some companies like Schneider are coming with ideas on DC microgrids, like having 230 volt to distribute power over 1 or 2 kilometers, right? However, this let's say this product you can only find in India. I could not find in other places. Other ideas that are coming also from the past, I have a very good friend, Kakigano, which has been worked for many years in DC distribution systems. And he believed at that time, this is a publication 10 years ago, that he could develop bipolar DC systems for houses. Because if you think about Japan, they are using one phase 100 volt, yeah, 100 volt. And then you can use, for instance, just if you have a bipolar system, just using a half bridge, you can have an AC current here easily. So a very simple converter, and very, very good reliability, let's say, because if one of these phases fail, you still have the other to support your grid. So I will say that this is not happening in the houses, even not in Japan or Korea. However, you can see in some places, like close to Lappeenranta in Finland, that they have a DC distribution system exactly as he envisioned. It's a bipolar system, plus minus 750 volt and 0, yeah, to distribute over different houses which are connected to AC inside, but with an inverter. And I will say that this is amazing. I can see also many other applications coming. I think I have some slides. I will come back later. Also in Europe, we had some cases of failure, let's say, like this old company, RE-Bus, which they come with a very good product. I will say technically it's very good. You know, it's to think about your house going to DC, and thinking a little bit more about this idea of having the voltage as a signal to regulate your microgrid. So you can see similar ideas as in frequency for AC grids. It has been applied in this amazing thing. So you can see if your, for instance, if your photovoltaic system is working here, means that the voltage is, let's say, in levels, low levels, let's say between 380, 400. However, you see that the voltage is going too high, means that you have too much power here. So automatically you will go and work outside your MPPT and drop down the power. This is exactly right now what we have in our inverters in our houses, looking at the grid, and they see if the frequency is going too high, they just disconnect it. First, decrease the power until there is a point that they disconnect. Especially this part is very important because this is the drooping part. We also developed some project some years ago. In that case was a collaboration project with Virginia Tech and also Japan. At the beginning of the project, many companies joined, like also was Bosch, trying to develop new devices working on DC for houses. But at the end of the project, companies dropped down. Some of the companies in Japan also enter in bankruptcy. So it was really a disaster from the viewpoint of that we could not see DC houses happening, but it was a lot of lessons learned from that. What you can see also, it's still happening in homes. Let's say that our electric vehicles, this is just one picture from my Nissan Leaf. We have DC chargers. In that case, what I have is a CHAdeMO. And this is very simple. So you have a plus and minus, 500 volt, and then these other pins are for communication. And then this is the AC part. So AC part means that I can charge the electric vehicle through an onboard charger. Of course, this onboard charger is slow, let's say, if you compare with an external charger. Normally, these external chargers are working on DC, at least if you think about the Japanese standard. And in that case, if you think about Denmark, what we have here are, a lot of them are produced by ABB, and they are chargers in the level of 100 kilowatt. Each of these 100 kilowatt chargers, if you have different plugs, you could charge 2 vehicles at the same time. So right now, imagine in many of these stations, maybe you can find one. Imagine the day that we will have 20 of these chargers. No, sorry, not 20, 20 cars. So 10 of these chargers. We are going to talk about 1 megawatt to support 20 vehicles charging, right? So this is something we have to think about, because at the same time, if you think, for instance, my car is from the generation of cars of 30 kilowatt hour, 40 kilowatt hour, but next generation of cars, they will surpass maybe 100, 200, or 300 kilowatt hour. And then what we are calling now fast charge maybe has to go even higher. So this is something we have to think about. Right now, we are just creating the problem, and I think it's exciting to do it this way. Other things also. At the beginning, I was thinking that bidirectional chargers were something useless. So I was thinking, why I need a bidirectional charger when I'm at home? There is no sun. When I'm at work, the sun is shining, and I'm just using the electricity to sell to the company of a low price, lower price than it's selling the same electrons to my neighbor. So my idea was, okay, maybe I can install a stationary battery, right? So this way, when you are not at home, you can just charge the stationary battery. When you come back from home, you can use it to charge your battery and also to provide your house. Right now, I think that things are changing a little bit, and we pass a lot of hours working at home, and this is not going to change a lot in the next years. So that's why I'm thinking, okay, I can use part of this electricity to charge my car, but then later on during the night, for instance, right now, like in Europe, it's right now, the night I have my electric vehicle connected, I can use the electricity for my home. And it makes a lot of sense. You can see we are talking about 6 kilowatt, so it's enough. You have to think that all our heating system is not electric anymore here in Denmark. It's just district heating created by a number of micro CHP units in the whole country. However, if you still want to go for, let's say, stationary batteries, it's okay. You can combine, I know some people that had for instance, old-fashioned grid-connected installations. This is not a problem. You can still combine with grid-forming inverters. This is just one example from Fronius. You could connect also more PV panels and additional stationary batteries. So you could create still your microgrid, even if you have a conventional grid-connected PV installation. Yeah, it's not like before. You have, of course, very expensive options, cheaper options, and something in the middle. Yeah. The next project we developed was together with Norway and Croatia to develop DC distribution systems for electric vehicle charging stations. And this was a very nice idea we developed. And the good thing of that is that you need some stationary energy storage systems, because when you have a number of electric vehicles connected, you need to be able to discharge peaks of power that are required by the car, and you could damn the grid otherwise. You have to think that a lot of them are using CHAdeMOS or similar in DC, so it makes a lot of sense to think about the DC system here. And even though we use flywheels for our project, it was another project in China that they were using Second Life cars batteries to put it in the electric vehicle charging station. So I think that's an amazing idea. Going a little bit further, when we talk about electric vehicles, not only we are talking about cars, but also we are talking about aircrafts, and also we talk about ships. So one of the examples is, for instance, the Boeing 787, which is having, let's say, kind of a small wind turbines. And this is not the main engines, of course, but those are starter generators that are supporting it. And inside we can see a number of microgrids. So in red, you can see AC microgrids in 230 volt, but then in green, you can see a number of bipolar DC microgrids. So the same idea of Professor Kakigano had for houses, right now you can see implemented in aircrafts with this plus minus 270 volt on DC. Also, again here, a number of DC microgrid systems and batteries embedded in this aircraft. We move a little bit further, ships. What is happening with ships? Also ships, you can see a lot of them going to hybrid or to electric. And in the case of ferries here in Denmark is amazing. I can see any ferry right now that is or pure electric or hybrid. So old-fashioned ones are basically disappearing. Yeah, and we have a lot of work right now retrofitting all ferries as well.
Dr. Guerrero,
yes.
Sorry for interrupting. How about we have like 5 minutes? Could you like summarize in like 5-10 minutes?
Sure, I can summarize it.
Yeah, and we have a couple of questions, so we'll try to take at least 1 or 2 questions at the end. Sorry again for interrupting.
No problem, no problem. But the same, I just want to finalize that the same thing that we are seeing in ships going more to DC, not because DC is more efficient, but because we can get some independence on the frequency and how the engines are moving, which is not happening in AC. And we can see also more interesting things also going in ports. So that's why I wanted to talk also about satellites, because in satellites we have also, I wanted to talk about many things, but anyway, we will skip. In the case of satellites, you can see that they are really, well, I don't have it here. We can see that they are really also DC microgrid systems, right? So you can see that from the Earth, sea, space, we are really moving to DC. Even, for instance, the International Space Platform, it is working fully on DC. In the past was designed on AC. Right now, everything is redesigned on DC. So that's all I wanted to show here. This is the last sentence. Thomas Edison, let's say the genius from DC. Genius, 1% inspiration, 90% perspiration. He was always trying. Yeah, never give up, I will say. Yeah, thank you.
Thank you. Thank you all for attending this event, and Many thanks to you, Dr. Guerrero, for the great presentation about DC microgrids. And I want to say I'm also a fan of Dr. House.
Thank you.
And before we take the questions, I just want to remind you about our next event. It will be about island detection in refinery configuration by Daniel Jones. He is a professional engineer at Power Engineers. It's a local utility here in the Palouse. And I want to note that maybe Dr. Guerrero could add to that. For non-IEEE members who joined us today, we encourage them to join IEEE. And Dr. Guerrero is an IEEE fellow. He knows the benefits of IEEE and joining IEEE in general. So we might have time for 2 questions, and I apologize for not being able to take all the questions. So I received 2 questions about what the time frame for charging the electric cars.
That's very interesting. Sometimes when we make a question, what is behind this question? Yeah, maybe some beliefs. And sometimes it's attached to something that we are doing. Before I start answering the question, you have to think that I didn't have car before, so I cannot tell you in the last, let's say 10 years, I didn't have car, you know. I live in the city center. It's not need for having car. Right now, I had to move to another place, which is more difficult. So when I compare this, having, let's say, an old gasoline car, I understand that you have your car place at home and it's doing anything. You go, when you need gasoline, you go to one place, you fill it, so you need it very fast, right? In the case of an electric car, when it is sleeping at home, it is charging. It is charging, so I don't care about the time, you know? When it's sleeping, it's charging. So try to don't compare it like this. I can tell you, I barely go to charge outside. So if I compare myself with a person who have a gasoline car, the one who have a gasoline car spend more time charging his vehicle than myself. Because for me, it's very strange the day that I have to charge. I mean, when I have to make maybe a long distance, it's true that I need it. But normal, daily basis, let's say, go to work, go to shoppings, etc. Even right now in supermarkets, we have chargers. So even you are shopping and at the same time, your car is being charged. Okay, so it's totally different. I can tell you that I'm saving time and money. I also made a comparison of money. It's amazing. Just starting, it's half of the price. And of course, if you produce electricity as I do myself, you can imagine that this is not zero, but it's really small. So I think I answered the question about the time. We told if you go to a fast charger, it can take you, depend, around 15 minutes sometimes. You can drink a coffee. You imagine you travel, I don't know in miles, because here in Europe we think on kilometers. But once you have been drive 200 or 300 kilometers, this means that 2 hours, if you are in the highway, 2 hours already passed. You know that it's mandatory, you must stop and rest every 2 or 3 hours. So it's good you stop, you charge it, you relax your legs and your mind, and continue. You understand me? So sometimes when you live in this society that everything has to be in high speed, you know, it's also not good for you, right? So also it's helping you to say, okay, already 2 or 3 hours, I have to stop because I don't have more electricity. And indeed, it's not good. I cannot get more attention. This is also connected a little bit about the brain. Let me explain you. We have this part the frontal cortex. It's like very small part, which need a lot of energy and gets tired very fast. That's why when, after you make some task, you're working and you're concentrating, you cannot last for a long time. Then what happens is that another part of your brain is activated, which allows you to do two things at the same time. You go to automatic pilot. You know what happens when you go automatic pilot? It's very prompt that you will have an accident, because you are just going. You know, sometimes you are driving, I don't know, you have this experience. You arrive to one place and you say, I don't recall to make all this road. I just arrived. What happened all this time? You were not here. You were in another. Yeah, there is a nice neural network that allows you to do that, but it's really dangerous because you're not present. So it's very prone that something will happen and you will not react. So it's very good to rest, you know. The car needs to charge, but you need to rest also. Sometimes we are just driven, you know, like, okay, I can full the deposit and I can drive 5 hours without stopping. That's crazy. So I will say, yes, I need time, but everything, and like my mom said, everything needs time, right?
Okay, thank you. I can combine several questions. I think what people are trying to ask is, what is the future? What, in your opinion, what is the future of DC microgrids? I've seen people asking about, does, for example, HVDC system will like make the DC microgrid case weak? And I've seen people talking about the controller, like using intelligent control to control DC microgrid. What, in your opinion, what's the future of microgrids?
All right. In the past, we thought that microgrids was something like a Lego, right? Something, or some, for instance, Lego is maybe a bad example, but something like you could buy and you could install, and there is like a place that you have a small wind turbine and then a photovoltaic system, then a battery system, you know, something like this, and you connect and it works. Today, we know that it's not like this. It's a philosophy of life, microgrid. So this means we try to generate, store, and consume close each other. And this concept is coming now not only with electricity at all, it's also with thermal storage. It's coming also with water. You can see something called micronets. You can see the same concept with food. It makes no sense that I receive food from, for instance, you people in the United States receive food from Europe. You should try to get the food next to your place because it's what is more sustainable. So we can see that all these DC microgrids maybe are not coming at home. Maybe they will come in some point, but they are not coming at home because we have an structure that already works. However, as someone said, HVDC is coming. And we know that it's coming because even though when you think about offshore wind, there's a lot of offshore wind farms that are on AC because the distance is relatively small. So when you talk about 50, 100 kilometers, maybe it doesn't make sense. You need at least, for instance, 200 kilometers to start to pay off. Right now, what are we talking about here? We are saying, for instance, in Denmark, we are building artificial islands to interconnect more wind farms that are really far away from here. So we need HVDC, more HVDC. And what else is happening with wind is like floating wind is also coming. And floating wind allow you to put in any part of the sea more wind turbines that we never dreamed before. So it's clear that when you have it far away, you need DC. And this is not killing microgrid. What it's doing is bringing microgrid technologies also to the sea, because those offshore wind farms also we can see today that they are starting to think on microgrid principles, like having possibilities to work in island, because I don't know if you are aware of that. Every time you have a problem with for instance, the cable or the main grid, and you have to disconnect the offshore wind to make some reparation, you need to put the offshore wind in island, you make the reparation, and to reconnect and to make a black star operation, you need to put a huge diesel generator polluting all the area to restart the offshore wind farm. That's really very crazy. So a lot of these concepts are coming in, also to have more grid forming units. So concepts that has been developed for many years in microgrids are now coming also there. I would say that they are really splitting. Or the examples I just give before, ships working on DC, they are coming more and more. And of course, all the examples that I give you in space. What kind of microgrids do you think that we will build when we go to Mars?
Okay. I think with that, do you think we can take one more quick question?
Anytime for me.
Okay. So because I saw it like two people ask about the controller for DC microgrids. So they are asking what type of controllers that you are, like, maybe you suggest. Like I see PID controller or combination or intelligent controllers. I see some people saying what is the alternative of droop control. Just your thought about controlling DC microgrids.
Yeah, that's a very good question. You know, when we are thinking about AC microgrids that are connected to the grid, you need grid compliance. You need to give frequency participation. You have to react. When we are thinking about DC microgrids, we can do whatever we want. Even if we are connected to the AC grid, we have a converter in the middle. So whatever the controllers you want to do are okay. I will say very agnostic on this sense. To say whatever you think it's good, it's good. Try to do it simple, double good. But I will say that there's many ways to achieve the control of a DC microgrid. So it's just on your imagination. I think that today we can see that we live in a information society. We have a lot of information, and the people, the more read, the less imagination they have. And this is normal. The more you read about something, your imagination is going down. So please, if you try to think about something, try to don't read. Just look, just do it internally. Do it in a microgrid principle. Disconnect, and think, and try to follow your beliefs. But maybe your beliefs are connected to something, so even disconnect from your beliefs, right? So I will not recommend you use this kind of control, this other, because every time you use something, maybe you improve something, you lose something, right? This is also called the whack-a-mole effect. Yeah, it's something very, very famous in Korea. You try to whack-a-mole, and the same mole appear in another part of the table. So I'm not close to anything. Is it better to use droop than other controllers? I don't know. Just try it. Just try to look at that, make it simple, and enjoy in the process. So I will not say anything. So automatic control, it's kind of something simple, right? Because it's a little bit, let's say, reptilian brain, action reaction. But when you think about intelligence, I think that this here is opening a lot of interesting things, no? How you operate, how you do these kind of things, how you look into the future and coming this back, and how you try to get the best of yourself. I think this is more difficult, and it's difficult to make it simple, because at the same time you have to be able to do very nice things, but that are able to be implemented in a very small place, for instance, right? So I will say that finally it's also that in the microgrid philosophy, it's inside. Try to reduce it in number of resources. Sometimes even I saw cases in which don't do anything is better than trying to do something, right? So try to make it more natural. So
less complex.
Less complex, exactly. So and why you try to make things complex? Because you are reading many complex things. So again, it's killing your imagination, right? So that's my advice. Don't read anything. Don't trust. We come back to the first slide. Don't trust a word of what I'm saying here.
Okay, so I would like to thank you again, Dr. Guerrero, for the amazing presentation. And we are honored to have you at the IEEE Palouse section. Maybe in the future you can visit us here on site.
Thank you. I will be glad.
Yeah, thank you all for attending this event.
Thank you, and have a
Have a nice
day.
weekend. You too, bye.
Thank you.